No, you don't hear him. Keep it back. When it comes, then you.
See my NASA flag?
Yeah,
Yes,
Okay.
that's awesome.
excellent.
Okay, ready?
Yeah.
Let's go.
Hi, guys. Thank you for joining. This is Essence of Science, and today we're talking about the end of the universe. I'm Amanda Armagost.
I'm Dr. Abbasi for Essence, and we have my good old friend from Houston or Texas, David. David, please go ahead.
Yeah, hi, my name is David Garrison. I'm a professor of physics and I've been studying cosmology and numerically simulating the universe or using supercomputers to simulate the universe for about 20 years now.
Wow, what an interesting topic.
So, sorry, what does that mean to numerically simulate the universe?
Okay, what I do is when I was in graduate school, I was at Penn State University and we were working on a project called LIGO, which stood for Laser Interferometry Gravitational Observatory. So what we were trying to do is we were trying to detect gravitational waves, and I worked on the numerical computational side of that, which is that we spent a lot of time trying to simulate the collision of black holes because that was thought to be the strongest source of these gravitational waves.
And we found one. When was it? 2011 or 8?
It was actually 2015, and it was really big because when we were working on this research, and we had a whole center for gravitational physics, and people were working on quantum gravity, people were working on different aspects of gravity and cosmology and black hole theory and all kind of stuff. And we go to conferences and people, thought we were doing a bunch of science fiction.
Yeah,
And
no,
then when we actually detected something,
yeah,
it changed the whole field. It changed
yes.
everything.
Now, LIGOs, they're the masterpiece of human technology. For
Yes.
people who don't know that, now imagine that two black holes collide. It sends actually a wave of gravity or is changing the fabric of the space-time. And in two places, I think one is in the north, one is in south in United States.
Yeah, one
That,
is in Hanford, Washington, and the other one is in Livingston, Louisiana.
yes,
And
and
then
there
there's
are,
also other sites that are from other countries. Like there's one in Pisa, Italy, and there's the Japanese had one, and there's one in Australia. And the idea is that when a gravitational wave passes by, it's really strong close to the black holes, but as you get further away, it gets weaker and weaker and weaker. And when it gets to Earth, it's incredibly weak signal. And so what a gravitational wave does is that when it passes by, it causes space-time to stretch and contract.
yeah.
So it's like
But
when a gravitational wave hits you, you get a little bit taller and thinner, and then you get shorter and fatter,
how
and you
much? How much
oscillate.
taller and thinner?
Well, about a part in 10 to the 20.
So it
So
is
that means
smaller than a proton.
if you take a one and you put 20 zeros behind it, or if you take a zero dot and you put down 20 zeros, that's how much it changes you. That's the fraction it changes you. So if you wanted to find a gravitational wave and you were to have this LIGO detector, which is two arms that are perpendicular to each other, one arm is going to get slightly longer than the other one by that 10 to the 20. So what that means is that if you want to detect something like a millimeter or so, something you can easily measure with a ruler, the arms would have to be several light years long. So they scaled it down to what the NSF was willing to pay for, and they got down to 4 kilometer long arms,
Uh-huh.
which is pretty big. I mean, you're thinking about it, that's several miles long these arms are. But when the wave passes by, the length of change in the arms is on the order of 10 to the minus 13 meters, which is it's smaller than the diameter. It's like a hundredth of the diameter of an atomic nucleus. So if you take an atom and you just look at the nucleus of the atom and you slice it into 100 different pieces, that's what they detected.
This is so amazing that we are able to do measurement like that. And the way we do that is that the lasers get reflected from a half transparent mirror. And when the dimension change, instead of interacting with each other in one way, they interact with each other in a different way. And all of a sudden we see there is more or less light. And then when you measure one in Louisiana, and whatever it's the space between Louisiana and Washington, and with that speed of light, you get similar kind of signal in Washington, then you know one of those waves just passed through the Earth.
Right, and the
It's
idea
amazing.
part of the idea of having more than one detector is that they can figure out where they came from, and they can also figure out how far away they are. So
Yeah.
when we actually detected something, it was literally like 1 billion light years away. It wasn't close
Wow.
by at all.
Yeah.
So
No, it is amazing that things like that even exist in the universe.
Yeah.
But I chose the subject that the title of this podcast for a reason, End of Universe, because I think that is very interesting topic for lots of people. That is universe static, like Einstein was saying, or is universe not static? Is universe expanding, contracting, expanding, contracting? Is it cyclical and so? I don't believe we really know the answer, or do we?
well, we do know, and the way we go about knowing it is we start off with the observations. And so if you look, you look out at the stars, and people have been looking out at stars for their entire human history. And, at a certain level, they're not much different than they were when the first people looked at the stars. But if you look at it close enough, you could start seeing little changes. And so a lot of astronomy is just built on seeing these little changes in the stars or where the stars at a different position in that. And so that's how they figured out seasons, for example. They noticed that the stars look different in the summer than they do in the winter because you're on a different side of the sun. And that's how we figured out that the Earth revolves around the sun. And then what we did was,
But we
over
killed some
time,
people who said that, right?
yeah,
Like Bruno, Giovanni Bruno was burnt literally at the stake to saying that, sun is another star. We are going around the star, and there are maybe other stars with other planets and people like us there and so on. He was literally burned at the stake for that, wasn't
yeah,
he?
it sounds really crazy because it's kind of like people say, oh, the world is round, and it's like, no, it did. I put my level on the ground and it's flat.
Our ability to deduct facts from observation is what makes science science. So,
Right.
But keep going. I interrupted you, but keep going. So we look at the star. Now, obviously, for a majority of what we have seen only stars in our immediate Milky Way galaxy, not even, all the Milky Way in the immediate surrounding and so on. But
Yeah.
go
So-
ahead. How do we deduct from that beginning and the end of the universe?
Yeah, so I mean, the idea is that we look back. So the further we can look into the universe, the further back in time we're looking. So when you start looking at stars with your naked eye, it looks pretty static. You could start to see some differences at different times a year. But then what happens is if you take careful records, so that people are taking records over their entire lifetime, and they're noticing these differences, and then they start inventing telescopes so they can actually look closer at the stars. They see that something that's really bright up there isn't really a star, it's a planet. Like for example, Jupiter. You have a decent, $30 telescope you buy online, you can see Jupiter. It doesn't take that much to really be able to see the rings.
They used to be called planets from Wanderer because they used to go, all the stars would move in one direction, but some of these star-like things, light in the sky, they would go one direction and then other direction and one direction and other direction, and would have no idea why they wander around. So we call them planets, meaning wanderer. And then we noticed that they are actually planet, but still, there are five. There used to be like what 7 planets and so on, and the moon was one of them. Sun was one of them, and then Mercury, Venus, obviously Mars, Jupiter, and so on. But that is all was for us. We had no idea. We had no concept of that. What that is. When did we even discover that we are part of a very average galaxy? When was that?
Well, and see, a lot of that comes from when you start mixing the physics with the astronomy. So not only you have these observations, but you get the physics to explain those observations. And that's how some planets, like I think the planet Neptune was actually discovered not because anybody saw it, but more like because they could see the effect of it. Like the solar system didn't really make sense in how the planets were moving unless there was another planet there. And then that way, that's why they discovered it. So I can't remember if it was Neptune or Uranus, but one of those was discovered that way.
I think it was Neptune.
Yeah, maybe
Yeah.
Neptune.
Yeah,
So the
just
idea
the
is that,
effect of the gravity, how the other star moved, it wouldn't make sense until you fit another planet, big planet, behind that. And then once we looked for it, then we saw it, right?
right, and they had to basically know where to look because this, the sky is big.
Yeah, yeah,
If you don't know where to look, you're not going to find it.
yeah.
So we look at these stars and we look back and we build bigger telescopes, and then we reached a point where we couldn't see any further because at that point, the light from the early universe or from that point in the universe hadn't even reached us yet. It's called a horizon. And we hear about horizons around black holes, but a horizon's any time where it's literally impossible to look beyond it.
Mm-hmm.
And so,
How far away is it?
oh gosh,
I heard different numbers, even though the age of universe as we think it is 13.7 billion, but the horizon is 93 billion, I have heard.
I think it's
across.
I think it was something like 30 billion.
Yeah, it
Wanna
is
say?
40. I heard it's 47 billion in each direction, which make total of 93 billion across the universe. But how is it even possible if the whole universe is 13 billion years old, 13.7 billion years old? How
Yeah,
can
that's-
it be like, how can we even get light from 47 or 30 billion years ago?
And that's where this whole idea of the expansion comes in.
Oh,
Because when they look back in time, they look back far enough, they saw that the universe appeared to be getting more and more dense.
mhm.
And when you get more dense, then at some point around when the universe was like maybe 500,000 years old, according to what we were able to calculate, or which is a fraction of the size it is now, it was so dense that light couldn't just move through it freely. And we had to use plasma physics to explain the dynamics of the universe at that point. And then
Mhm.
if you go back even further, you have to use high energy particle physics to explain what the universe was like. And then you go back even further, it looks like you need some kind of new theory like quantum gravity or something to explain it. So what I do in my research is I actually go all the way back as far as we can go with known physics. That's stuff that we've experimentally verified, which
How
is
far back is that?
it's when the universe was around 10 to the minus 12 seconds old.
Okay, I cannot even fathom that around my mind.
Yeah, at that point, the universe was 10 to the 16 times smaller than it is now. So imagine a trillion, but then you got 10,000 times more than that.
So what was the size of the universe at that point?
At that point, if I wanted to model the entire visible universe, it would fit, well, it'd fit on Earth pretty easily. It would
Okay.
fit within around 10 about 10 to the 11, 10 to the 12 meters, which is around 1 billion kilometers.
Yeah. How do
Actually,
we even know that?
yeah. So actually, no, it's still between the Earth and the Moon, I think, is
Yeah,
somewhere.
yeah. But how do we even know that? I mean, I mean, this is just unfathomable. A fraction of a nanosecond after the Big Bang and these sizes and so on. How do you guys come up with these numbers?
Yeah, and see, that's the thing. We just go with the consistency. And what happens is you have to apply general relativity, which explains the fabric of the space-time and how it's expanding. And then at that level, you have to start applying plasma physics, and you have to even use relativistic plasma physics.
Mhm.
And so what happens is at that point, everything, the best I could explain it is that it gets very consistent between the physics, because at particle physics, they look at what happens at very high energies when the
Mhm.
universe is really, really young, and there was
And
a lot of
hot.
particle collisions.
Yeah.
And you have to look at, well, what elementary particles existed, what were their dynamics, what were their charges, all these things.
This
And
I want to come back to that,
yeah,
what particles really exist. Now, but before I do that, what makes you so confident that the universe is expanding? What evidence do physicists have? I know it is a fact, but at least at
yeah,
this point, but what fact do we have confirming that the universe is expanding?
yeah. The strongest evidence comes from the redshift. So what happens is whenever you have a distant galaxy and it's moving away from us, then because it's moving away, you get a Doppler shift effect, which means that it's going to be if you assume the physics of that galaxy are exactly the same as the physics of this galaxy, then you would expect it to be emitting light at a certain frequency. But the light is redshifted, so that means that it's moving away from us. And then we notice that the further away they are, the more they're redshifted.
Mhm.
And
Now,
the neat thing here
mhm.
is when we started seeing gravitational waves, those were redshifted too.
Wow, wow.
So they get redshifted just like light does, because
Mhm.
they're moving through the same expanding space-time.
Yeah.
And so for consistency, the only thing that could really explain this redshifting effect is this expanding space-time. And that's what really explains it well.
Yeah.
Either
No,
that or the
yeah,
physics of distant galaxies is just completely different than our
yeah.
physics.
No, well, for our audience that they don't lots of words about the redshift and so on. Now, the best way is you get a prism, you put the prism at the sun, and it breaks down the color of the light from our sun, and then you see these individual colors. In these individual colors, you have literally gaps, dark lines, and these dark lines when we know they are coming from hydrogen, just the main things that practically produce light in certain ways from our sun. And when we look at these lines from our sun versus another sun that's close by, we see the same lines because the distance is not that far and you're not moving away from each other that far. But once we start looking at this light of the stars, which based on our understanding, they all produce light in a certain way, we see that they're stretched. These lines are moving in the red area of the spectral line. That's why we call it redshift. And we see those galaxies that are farther away, they're stretched even farther to the left, indicating that those galaxies are not actually stationary, but they're actually moving away from us. As a matter of fact, there is a distance beyond that. Those galaxies are moving away faster than the speed of light. How is that even possible?
Well, it's because the whole speed of light rule only applies when you're moving through space-time. It doesn't apply to the space-time itself. So
Space is stretching.
so there's a cosmic loophole that basically says if you want to go faster than light, you have to stretch the space-time And there was actually something that somebody came up with called an Alcubierre warp drive, which was made to explain the warp drive that you see in Star Trek.
Would that work? Would that work?
They know the physics behind it. In order to make it actually work, you need negative matter, which
Ah,
nobody has.
yeah, yeah. They talk always about antimatter chamber and so on, and nobody really understand. But no, seriously,
Mhm.
if we had negative matter or antimatter, and would the Star Trek warp drive work if we had antimatter?
Well, it's not we do have antimatter, but that's not negative matter. When we talk
Yeah.
about negative matter, we mean
Oh,
negative
oh.
mass. Like it would be something where if you had a pound of it and you dropped it, instead of it falling down, it would actually go up.
Wow, anti-gravity.
Yes.
Wow, no, that I have never heard of that. Okay, so is it science fiction so far?
Yeah, that's still science fiction because we have no idea how to make negative mass. And you can write it in an equation, but actually producing it, like physically making something like that, doesn't work.
Okay, my head's already spinning now. So let's go back there. We know universe is expanding, and some smart people like Hubble, they looked at different galaxies, not stars. They found
Mhm.
out farther they are, faster they are moving away in every direction. Now it's like a clock. Turn the clock backward, and then they must have been closer to each other in the past. They come together, and somewhere around 13.7 billion years ago, they must have been, entire universe must have been in one place. And then that's what we are talking about, exotic matter and things that nobody really knows what they are.
Yeah,
Tell me about
and see, that's the thing. Nobody really knows how it started at that point. There was actually a guy named Lemaitre who first came up with this thing called the Big Bang Theory. And Hubble was able to experimentally see this. He was able to look at his telescope and see, wow, this thing's expanding. It must have come from one point. And that's one of the reasons why I only go back to the electroweak phase transition when I'm doing my simulations, because I can't go back any further without really doing a lot of speculation on what the universe was like at that point. There's different theories. Like there are theories about modified gravity, there's theories about quantum gravity, there's theories about all kind of exotic things, and none of it has been anywhere close to experimentally verified.
So is it safe to say when you get to the point that you are, our current physics really breaks down and is not applicable anymore when you
Well,
get that close to the Big Bang?
yeah, when you get closer, when you're at the point that I'm starting my simulation, it's still, we've got some experiments in high energy physics and stuff that verifies that. Even when we talk about inflation theory, which was this idea that the universe went through this super fast accelerated expansion really, really early on, that hasn't been verified experimentally, or there's been no experiments. It's still just a theory on
Is that
that.
Alan Guth theory?
Yes, Alan Guth's theory of inflation.
Yeah. No, that is practically it says that universe, whatever, started somehow in a fraction of a nanosecond. It went from a size of a pinhole to a ginormous size. It grew so much faster than the speed of light and created all the universe we know. And then after that started expanding with the speed we know. How close to the origin of the, I mean, time-wise and so on, how close does your physics go to the origin of Big Bang?
Yeah, see, I think that the inflation there would have been around 10 to the minus 35 or 38 seconds or something like that. So
Oh, that is,
it's an immeasurably small amount of time.
yeah.
Like, I don't think there is a clock on the planet that can parse out that short amount of
Yeah.
time.
Okay. Well, then we started to grow, and then all of a sudden, universe was immensely hot. It got cooler, but it was still hot. But it was all of a sudden cool enough for the light to be able to escape from it. And that's still very hot. and then it cooled down like any gas, thermodynamic, any gas that expands cools down. We went from that unfathomable heat to a natural temperature of the universe right now, which is what right now?
Yeah, so what basically happened is you got to keep in mind the universe was made out of different stuff. So you've got all of this energy, like radiation, light that was there, and that made up a lot of the universe initially. That's why we called it the radiation dominated part of the universe. And then you got regular matter that we're made of, you know,
Okay.
that's hydrogen and oxygen and all these other different elements. You could think of it as the us part.
Yeah.
And then
All
you've
of us except Amanda. Amanda is made for special matter.
and then you've got dark matter. Dark
Okay,
matter,
okay. Dark matter. What is that?
we don't know. That's the short answer.
I was getting excited.
There's a lot of theories about dark matter and what it is, but as far as we can tell, it's matter that interacts through gravity, but it has zero interaction through electromagnetic means, which means that light passes right through it. It's not really dark, it's invisible.
Okay.
So light would pass through it. If you were to touch it, you wouldn't feel it because there's no the reason why when you put your hands together and your hand doesn't pass through your other hand, it's not because your hands are that solid, it's because of the electromagnetic interactions between the electrons and the atoms in your hand. Well, dark matter doesn't have those interactions. So if you had a pound of dark matter, your hand would just pass right through it.
Yeah. Doesn't sound like neutrinos?
That's what they thought. They thought neutrinos could have been dark matter.
But it is not?
The estimate now is I don't think they believe it is, or they don't believe it's the whole picture because it doesn't seem like they can account for the amount of dark matter we're seeing.
Okay, well, we are now. I want to know. I really want to know. Now, we have regular matter, and we have dark matter. We have regular energy and we have dark energy.
Yes.
Okay, and
so
then
that's
100% of the universe. Break it down for us.
Okay, so we know regular matter, we know regular energy, and that's one of the things that the regular energy drove the expansion of the universe at the beginning. And so this thing we call the Hubble constant, we've all heard of. In physics, we don't call it the Hubble constant, we call it the Hubble parameter. It's only been a constant for our lifetime. The rest of the age of the universe, it's actually been changing. And if you look at it over the age of the universe was expanding really fast. And the Hubble parameter is a measure of how fast the universe is expanding. And it slowed down as the universe expanded. And what's happened is that when you take all this radiation, this photons, this electromagnetic radiation, when that expanded, the density of it died off really, really quickly. So then matter became dominant because the density of the radiation died off faster than the density of the matter. Then what happened was the density of the matter also dropped off, not as fast as radiation, but it did drop off too, with the idea that eventually, if there was no such thing as dark energy, matter would just drop off in density until it eventually gets to zero effectively, right? Well, dark energy is this little thing that in my simulations I did, it's actually something not new, but it's actually been around from the beginning. And I modeled it as the cosmological constant. And the cosmological constant is a very interesting thing where somebody figured out,
well, someone was Albert Einstein, right?
Yeah.
What happened he said that was his biggest blunder, but it ended up to be actually his biggest insight.
Right. Because what happens is when you look at the equations of general relativity, in order to make the equations work, he came up with these Einstein equations. And it was basically when you solve these Einstein equations, both sides, you can see that you get a conservation of energy type thing comes up between both sides of the equation, which tells you it works. So what happens is that you figure out mathematically that you can insert a parameter into Einstein's equations where there's this term called the space-time metric. And if you put a constant times a space-time metric, you can throw that into that equation, and it doesn't change the effect of this conservation energy thing working, because basically you take this this mathematical function of both sides and you still get, it still lines up. So there's no reason why you couldn't have this parameter in there. It's no reason to say it is there, no reason to say it's not. Well, what happened is we're able to measure what this parameter is.
Okay.
And it comes out it's not zero.
And that was surprise though.
That was
when they
surprise.
found- yeah. And
But
as
the
a matter of
thing
fact,
Yeah.
the thing was that Einstein had this beautiful theory, and some other people made the mathematics for that theory. And when they put everything in, a tiny piece was missing. That tiny piece was missing was needed to make the universe the way Einstein wanted it, to a static universe. That piece was just missing, and he just came up with that thing, we just manually we just added to that to keep the universe static, to keep the universe as is, because he couldn't believe that what's going to really happen, that the universe was expanding and so on and so forth. And and many years later, we found out that missing part is not actually a missing part. Tell me, I have heard that is actually the energy of the empty vacuum. Is that correct?
Some people think it is. I think it's just, I just put it into my equations as just curvature, like a static curvature. And early in the universe, if you use the same parameter, because it's a constant, it's a real constant, not like the Hubble constant. And so what happens is, for the parameter to work, it can't depend on any other variables. It can't depend on position. It can't depend on time. So when you throw it in there, it's really tiny, and it has no effect early in the universe on the expansion of the universe. But when the density of radiation and the density of matter drop off enough, then it starts to shine.
Okay.
And it literally keeps the Hubble parameter going. So the Hubble parameter in my simulations, it starts off really high at the beginning of the universe, and it drops off, and it drops off as the universe gets less dense, and then it levels out. So the universe keeps expanding. It doesn't stop expanding, and that's it.
Well, let's come back to that. Universe is made of dark energy, dark matter, regular energy, regular matter. What percentages?
Right now, and the thing is, the percentages change as the universe expanded, but the dark energy is really the dominant thing right now. And I think it's like 70% of the universe.
So 70% of the universe is something we call dark energy. We have no idea what it is. Lots of room for speculation.
So,
Amanda.
okay, this is a question that I have. It's just a theory that I have. Dr. Abbasi shuts me down every single time I give it, but you're kind of helping me out with this dark matter thing. So the periodic table, is there any possibility that there may be an element that we haven't discovered yet?
I'm not a chemist, so there's probably some elements that we haven't discovered yet, but they're probably not stable. As in, they might only exist for like a fraction of a second.
They're still not dark matter, because anything on the periodic table would be still a regular matter.
Right. Dark matter, they think it may be caused by some other interaction of subatomic particles, which would not be like atoms like we would observe. So they wouldn't be on a periodic table in chemistry.
You're on my side.
No, actually, high five, David, because you're on my side.
Well, we both think you're on our side.
And that's how politics works.
Okay.
Yeah, right.
Okay, so 70% dark energy, we have no idea what it is. It just pushes the universe apart. What else? 30%.
Okay.
We have 30% left.
Okay, so 65, maybe it's 65%. So let's say 65% dark energy, 30% dark matter.
That's almost the 95% of the universe.
Yes. And then 5% is regular matter.
So we understand or we know 5% pretty much.
Yes.
As a matter of fact, there is a book. It's called The 5% Universe.
Mhm.
That book is just about that. Everything you see, you touch with your telescope, the farthest reach of the universe it's only 5% of what the reality is based on.
Yeah.
That is mind-boggling.
That's
Yeah,
insane.
and so it's really crazy. Like, I'm not sure about if it's 70 or 65% or something like that, but regular, the regular energy, is almost zero now. And so the dark matter, the funny thing is dark matter, it's like 5 or 6 times as much of that as regular matter. But yeah, we know nothing about it. We've observed it through gravitational lensing.
The effect
We've
of
observed
it.
it through looking at the rotation curves of galaxies. And I mean, they may be falling into black holes or something, but otherwise, we have no idea.
So universe is now, we know that started Big Bang, expansion, first inflation, then expansion. We are here now. The regular temperature of the universe, I have heard 3 Kelvin, which is extremely cold. It is like minus 270 Celsius, like minus 400 something Fahrenheit. It is at 2.7 or 3 Kelvin, very, very cold, but is by far way above the what we call absolute zero.
Yeah.
And we know universe is expanding more and cooling down. So now we are 13.7 billion years into it. Let's go in 13.7 or let's say 13 billion years in the future. My best knowledge is not really much change in the next 13 billion, but then let's go scale it up. Let's go to 13 trillion years. Tell us what happens.
Well, we're not going to be around to see it.
We are not, but universe will be around.
Yeah, the universe is going to be incredibly cold at that point, incredibly spread out. The problem that you run into at that point, and keep in mind, we dropped from 10 to the 15 Kelvin. So that was 1,000 trillion degrees Kelvin down to 3 degrees in the last 13.7 billion years. As you move forward, and I've actually got some simulations where I just let the thing run. When we get into, trillion years in the future, the temperatures drop down a lot, and the density of the universe has dropped down a lot to the point where the problem that we run into is that at some point the things decay. So stars die, and when they die, if they're spread out too much, there's not anything near them, you can't grow new stars. And so all of these nebulas that make up where these stars are being born, they eventually get so spread out because all the matter is so spread out that they just don't function anymore. And then at some point, people believe even protons might decay. So when that happens,
that's far in the future.
Yeah, that's far in the future, and that's more in the particle physics realm, which is not really my area as much.
Yeah.
But yeah, we're constantly expanding, and so the expansion rate of the universe is just going to keep going and going and going, and things eventually just kind of freeze out.
Yeah,
they don't rip apart. I don't think it's so much a rip, but it's more like
but some people do call it the Great Rip. Actually, that's a word some particle physicists and some astronomer they discuss. They say, we are moving so far away from each other that in few 100 billion years, or even maybe 1 trillion years, all the galaxies are so far moving so fast away from us, their light cannot even reach us. Meaning, if we then look into the universe, if we are there, probably we are not, we think the Milky Way is the only galaxy ever. But then stars start dying. Bigger star die faster than smaller star, and then neutron star, quasar, and so on. They all cool down, and then all of that eventually goes away, and then all what's left are some black holes. We thought black holes are forever, but now we know they have something called the Hawking's radiation, meaning very ever so slowly they as well lose mass and energy, and then they go up with a blip, and then even they are gone. It's all what's left. It's a vast, empty universe.
Yep.
What is the temperature of that universe, David?
Wow. That temperature could go all the way down to 0 or just above absolute 0.
Okay, well, that is what I want to talk about, because there is a good, I have been thinking about that for a long time, and that's an interesting concept, that the temperature of the entire universe get closer and closer to the absolute 0. And that absolute 0 is a fantastic number. Now, do you want to talk about what happens when like a bunch of helium atom get close to the absolute 0?
Yeah, and this is what people have actually been doing this in a lab, because
Yes.
they use a technique called laser cooling,
Yeah.
where they will cryogenically cool atoms down as far as they can go, and you can go down to 1 degree Kelvin with liquid helium and all these other sources. But then once you get to that point, what they do is they use a laser, and temperature is a parameter that is like the average energy of stuff. So what happens is it's an average. So if you take out the more energetic particles, then the average drops. And you can get down to what they call the millikelvin range, where you're like literally 1,000th of a degree above absolute 0.
But even macro kelvins, maybe even.
Yeah. And so what happens is when you get down to that cold, there isn't that internal energy in the atoms that are causing them to get excited and move apart. So they kind of clump together.
Okay, what does that mean? They clump together. What does that mean?
Yeah, so this is what they say is that atoms, like most of the matter that we run into today, they're called fermions. And that means that they're a particle that has a half spin, and it's a quantum mechanical property. If you take something like a photon or light, it has an integer spin. So it's got either 0 or 1 or 2 spin. Like a graviton, for example, they think is a 2-spin particle. So all the things that are force carriers are called bosons. And they have integer spin, where all of the things that are like matter, like us, are made out of things that have half integer spin. So when they get close enough, what happens is you got these two atoms and they have half integer spin, and they clump together, they come together, and they form a particle that has a 1 integer spin.
They become one, right? That's what
Yeah.
it more or less is. For layperson, is like you're there, I'm here, let's say we are atom, we are two distinct things. If you cool us down that close to absolute 0, or we say everything is a wave form, everything is based on Schrodinger and quantum physics is a wave. You and I, we become one. We are becoming indistinguishable once we get that close to absolute 0. And there is a name for that. It was actually a theoretical thing that somebody named Bose sent a paper to Einstein, and then he worked on the paper, and they published the paper, and we called that's a state of matter. We call that Bose-Einstein condensate. When you get the matter that cold, individual atom, they're not there anymore. They are not individual atom anymore. Everything together become one, and you cannot distinguish them from them. The so-called Bose-Einstein condensate, correct?
And here's the thing that's really interesting about it. When you get to that point, they become bosons. They're no longer fermions. And that means that boson physics applies to them instead of fermion physics. Fermion physics is really interesting because it basically, fermions, you can't have two things at the same place at the same time. So they can never be in the same place. However, with bosons, like photons, like you can put as many photons as you want in the same place. You can do that with these bosons now. And
Like,
now all this matter can literally be in the same place at the same time because they're clumped together in pairs.
like you and I can be inside of each other. We are not distinguishable. Like I can push you now, but then in that cold, we could literally be in one space. In that world, we wouldn't be living if that cold, everything's that cold. But our atoms, our existence, our matter, they wouldn't interact with each other like a regular matter, but we could be all in one. Now, David, has been a big question in my mind. When the universe becomes that cold, everything that is in universe, is it more or less like a Bose-Einstein condensate?
I think it can be. I mean, I think that at
But
that
that's the
point,
beauty of it. What I'm
Yeah.
getting at is that, universe is cooling and everything is separating, and all of a sudden the entire universe become Bose-Einstein condensate, and everything become like bosons. They are not fermions anymore. Is it the point at that point that space and time and so on, they just change the direction? The big space, because it is all one, become again like a tiny things, then explode somewhere else and another universe start? Is it possible?
well, that's a good question, but keep in mind that when that happens, matter's still going to be pretty spread out. So it would take a while before, if they could even come together in the same place. So you'll have clumps of it in different places. And then at that point, I mean, you've got a whole different looking universe because you don't have, like what we have now. And people have actually theorized about whether or not boson stars exist, like an actual star made out of these bosons, because we know we have neutron stars, right? Where the entire star is made out of basically neutrons. Now, is it possible to have go a step further and create a boson star? That's something that'd be really interesting.
Okay, well, when you are that cold, that close to absolute zero, or at absolute zero, do we have an understanding what space even means at that level? See, one helium atom, another helium atom, 100 other helium atom. They're in one physical space.
Mhm.
You cool them down to absolute zero. They become indistinguishable. What about the space that is between them, or what does that at that temperature? What does space mean?
That's a good question, and that kind of comes to quantum gravity, and that's one of the motivations behind why people think that there needs to be a quantum theory of gravity, because the idea of space is effectively comes from relativity. The idea of space doesn't really exist very well in the quantum world, because you can have two, like in a superconductor, they have these things called Cooper pairs, where this is what happens is that you cool down a superconductor the right amount, and then two electrons, which are fermions, kind of merge into a boson, and then they can move through the superconductor uninterrupted because now they're a pair. But the thing is, if you look at how far apart they are compared to their size, it's like if they were two people, it would be like they're on different sides of the earth. Like one is in China and one's in the United States, and they're
they're
somehow
paired.
locked together as a pair. So at that point, what does distance really mean? And then, so like this is one of the many things that kind of motivated people to start thinking about, well, how do you quantize gravity? And recently, Roger Penrose came out and said, well, we're thinking about it backwards. We shouldn't be thinking about quantizing gravity. We should be thinking about gravitizing quantum mechanics. And actually to make, to understand how the quantum mechanics actually works, like what happens when you collapse a wave function. Is it actually a gravitational process? And how does quantum mechanics, how does things like time and distance play in quantum mechanics?
David, we have few minutes, but I want to just ask you a general philosophical question.
Mhm.
Why lay people, why do people should even care about everything we talked about? Why should we care about all of that? Why is it important for us as a country spending money on, we spend a lots of money, in my opinion, not much, not enough, but why should we spend billions of dollars on those instruments to do research on what you and I are talking in the last hours?
Well, some people believe that the whole point of life is to understand why we're here and what we're doing and where we came from. And if you don't have that kind of outlook, it's sort of it makes things feel kind of meaningless.
Mhm.
And I think that what we do in a lot of ways is that we kind of give people at least making progress in understanding the universe around us. Like our view of the universe is very, very different than people who lived a few thousand years ago. And we know things that they could not have even imagined.
Mhm.
And the hope is that people who are here, in the future, in a few hundred years, are going to know a lot more than us. And if they haven't, if they are still in the same place that we are with the same understanding of the universe, it seems like that would be kind of sad that they really haven't progressed. And they still, I mean, one question people have is that, like, is there other life on other planets? And they're thinking, and if you don't really understand more about the universe and you don't understand the distance to the other planets and you don't understand what's going on out there, you can't answer that question until we saw exoplanets.
Mhm.
And we really did not know that there were planets outside of our solar system. We assumed that there were, but there was no evidence of it.
Yeah, I totally agree with you with everything you said, but let's say for people who are listening and they're still not convinced, they're totally materialistic based people and so on. Let me give you, on top of what just David said, another reason why we should spend money on this. Because if we don't, other countries are going to be the people who are going to have a fission power plants and make our economy meaningless.
The
Mhm.
more you learn, the more you grow.
And knowledge is power, and all our power, wealth, and sophistication comes from the basic science that David is doing. And if we stop being on forefront of it, soon we will become irrelevant. So I hope that is the reason for even on the other side of the spectrum that they don't have the curiosity. They don't want to know where we've come from, and they think only about the next 5 to 10 years. Your stock market value will be irrelevant when other countries overcome certain scientific hurdle that takes our economic power away. And if you don't spend the money here, if you don't do research here, you're on a path to become irrelevant.
Totally
So,
agree.
and that is not for you because
Mhm.
you have the curiosity. But for other people, I think it's important. It is 2 o'clock. I could spend another 5 hours with you, David, but we have unfortunately another meeting. So I would want to thank you. And I hope this is just a start of many of our podcasts together. But I think it's time to say goodbye to our audience.
Thank you
Right.
guys for watching. This was Essence of Science, and we talked about the end of the universe. I'm Amanda Armagas.
I'm Dr. Abbasi for Essence. End of universe is far away. Don't be scared for now. And our special guest, I'm very thankful for you to be here. David, please introduce yourself.
Yeah, thank you very much. I'm David Garrison. It's been great talking to you.
Thank you.
Thank you guys, and thank you, David.